In this module, we will begin to talk about the mathematical models, the mathematical tools that we will use for modeling physical systems. Some of you may find this module a little challenging and a little intimidating. There will be a fair level of math. It's a little abstract, but I encourage you to just hang in there. These are tools that we will be using throughout the course of the semester, and they will help for us to sort of build intuition. They'll allow us to sort of prove to ourselves ways to understand physical models. So it's not the math itself that's important, but it will allow us to sort of build intuition. Another aspect of this that I think is helpful is, even if in your everyday job you're not going to use this level of mathematics, chances are you do interact with people that do use these mathematical tools, that do that sort of detailed level of work, whereas maybe you work at a higher level or sort of a project management level. And by sort of gaining some familiarity, it makes you sort of less intimidated by these people, and it makes you better able to communicate with them. So even if you don't have to do it yourself much, you've done it in the past, you understand the idea. Specifically, we're going to look at differential equation models of physical systems, and we're going to use the Laplace transform as a means to solve the differential equation. Later in the course, we will talk about an alternative type of model called a transfer function. So here is a physical system, a mass spring damper, and that differential equation shown next to it models the behavior of that mass spring damper. This equation is classified as a differential equation because it has derivatives in it. It has a function x, as well as the first derivative of x with respect to time and the second derivative of x with respect to time. The way that we're going to sort of show derivatives, or sort of a shorthand, is to use this dot notation. So a single dot represents the first derivative with respect to time, and a double dot represents a second derivative with respect to time. So that's what that represents. This type of differential equation in particular is called a homogeneous differential equation, and it's classified by having the right-hand side of the equation equal to 0. So the left-hand side, you have it's a function of the function x and its derivatives, and the right-hand side is 0. And what this represents is it represents the free response of the system. So there's no external force being applied to the mass. You just give it some initial conditions. So you can imagine that you take the mass, pull it back, give it some initial position, some initial velocity, and let it go. This differential equation then captures the movement or the displacement of the block x, which is x. Looking at this, ultimately we want to solve this differential equation. We want to find the function x that is the motion of the block. For a given set of initial conditions, how does the block move? And looking at this, we see that our function x needs to be proportional, linearly proportional to its first derivative and its second derivative. Or it needs to be, the function x and its first derivative and its second derivative need to be a linear combination of each other that sum to 0. And so if you think back to calculus about what types of functions that might be true of, the one that comes to mind is an exponential. The derivative of an exponential is another exponential. And so it turns out that in this case the solution is the sum of two exponentials, one with an exponent lambda 1 and another with an exponent lambda 2. These exponents are solutions of the characteristic equation, are roots of the characteristic equation, which I'll explain on the next slide. But if you want to see why it is that those exponents are roots of the characteristic equation, you could, as an exercise, take this function of x of t and plug it into the differential equation and see what drops out. Another type of function whose derivatives have the same form are sinusoids, or sines and cosines, and we'll see how sines and cosines relate to these exponentials in a little bit. So here again is our homogeneous differential equation. The corresponding characteristic equation has this form, where the characteristic equation is a polynomial where the degree of the polynomials depends on the order of the derivatives. So the second derivative, x double dot, corresponds to lambda squared. The first derivative, x dot, corresponds to lambda to the first power. And if we had a third derivative, then that would correspond to lambda cubed, etc. And so again, thinking back to earlier math classes, how do we solve a quadratic equation like this? The way that we solve it, or find the roots of it, is to use the quadratic formula. And so the quadratic formula has this form, if you might remember. It's minus b plus or minus the square root of b squared minus 4ac divided by 2a, where a is the coefficient in front of the squared term, b is the coefficient in front of the lambda term, and the c is the constant term. So solving this equation gives us the two roots. That's why there's a lambda 1 comma lambda 2. The one root occurs when we use the positive sign, and the second root comes from when we use the negative sign. Looking at this, we can end up with sort of two different kinds of situations. We could end up with a situation where the roots are both real, if the value underneath the square root is positive, but we could also end up with roots that are complex if the quantity underneath the square root is negative. A square root of a negative number gives us an imaginary number, thereby corresponding to complex roots. So here again is the form of the solution. So this is how the displacement of the mass will change with time. If the roots are completely real, then the solution is exponential. And if the roots are negative, then we get exponential decay, or what we call a stable response. So for example, if we solve the roots of our characteristic equation, we solve for lambda 1 and lambda 2, and we got that lambda 1 was negative 3 and lambda 2 was negative 5. The displacement of our block would behave according to this equation. And so the graph of this is exponential decay. It looks something like this. You can imagine you pull the block back and it just sags. The spring pulls it back, and the damper damps it out. And we define this to be stable. When you give the system some initial condition, it returns to an equilibrium. It returns to some fixed position. If we solved for the roots of the characteristic equation and any of the roots were positive, then we wouldn't have exponential decay. We wouldn't have e to the minus 3t. We would have e to a positive number, e to the plus 3t. And so instead of exponential decay, we get exponential growth, and that indicates that the system the system continues to move forever. It doesn't reach some equilibrium. It just keeps moving off to infinity. And so we define a system like that to be unstable. So this is just an introduction. I don't really expect you to have a good understanding of what stable and unstable means, but it's an important concept that we're going to come back to, and I just wanted to start to introduce it. You can imagine that if we're trying to design a cruise control for an automobile, we would like it to be stable. If I give it a command of 55 miles per hour, we want the the car to approach some stable speed. We don't want the speed to grow exponentially. That would be bad. If the roots are complex, then we can rewrite the solution using sines and cosines. So if our lambda 1 is complex or our lambda 2 is complex, we'll have an exponential with a complex exponent. And we can rewrite that using this equation here called Euler's identity. And if you're not comfortable with that, that's okay. It's not something that you're going to be tested on. I'm just trying to explain to you why the form of the solution looks the way it does. So here's our x of t. We have our exponentials with complex exponents. Again, if you think back to earlier math, you may remember that if you're multiplying two exponentials with the same base, the exponents add. So each of those exponents can be split. The e to the minus the minus sigma plus omega dj can be split into two terms, because when you multiply the exponentials, the exponents add. And so each term has a common e to the minus lambda t in it. We can factor that out, and then we can replace the two exponentials with complex exponents using Euler's identity. If we rearrange things, we get this form. And this is what I was sort of alluding to before. Just like exponentials, their derivatives turn out to be exponentials again. Derivatives of sines and cosines also have the same form. So this is the type of solution that we get when we have complex roots of the characteristic equation. So again, this is our mass spring damper system. When the characteristic equation has complex roots, this is the form of x of t. So looking at this, try and think about what the response of the block would look like. What is our graph of x of t going to look like? What we have inside the parentheses is basically a sinusoid with frequency omega d, and we're multiplying that by a decaying exponential. And so the result is a decaying sinusoid. You have some oscillation where the frequency is the omega d, due to the term inside the parentheses, and then you're multiplying that by a decaying decaying exponential. So you can imagine that there's some envelope where the amplitude is dying off according to that exponential e to the minus sigma times t. So in this situation, if our value of our spring stiffness and the damping in our dashpot were chosen in such a way to give us complex roots, then when we pull the mass back and let it go, it won't just sag to the equilibrium, it'll bounce back and forth for a while until the oscillation dies out. And so looking at the root of the characteristic equation there, lambda, it has a real part, minus sigma, and it has an imaginary part, omega d. And each of those pieces of the roots tell us about the response of our physical system. In particular, the real part tells us how quickly the oscillation dies out, and the imaginary part tells us the frequency of oscillation. And so this is new. It may be a little hard to sort of come to grips with at first, but this is something we're going to hammer over and over throughout the course of the semester. We want to be able to look at a mathematical model, look at the roots of the characteristic equation, and understand things about our system. How fast does it react, which depends on the real part of the root. How much does it oscillate, which will depend on the imaginary part of the root. So these are important for when we analyze any sort of physical system. What would happen if the real part was 0, if sigma was 0? Think about then what our response would look like. If sigma was 0, then we would have e to the 0, where e to the 0 is 1. And so we would in essence just be left with that sine and that cosine, and so it would oscillate forever without decaying. Here is another type of differential equation where the right-hand side is no longer 0. In essence, this is a differential equation that's being forced. There's an external force F that's being applied to our mass now. The solution of this type of differential equation is a little different in that it has two parts. It has an x sub h and an x sub p, or which we're going to call an x sub h and an x sub p, where x sub h is the homogeneous solution. It's basically what we've already done. It's the solution of the differential equation when the right-hand side is 0. And that captures basically the natural response of this system. The x sub p is due to the forcing function, and it's called the particular solution. And it tends to have the same form as the forcing input. So if I'm forcing my mass with a sort of a sinusoidal force, or a force that's oscillating, then the solution of my differential equation is also going to have an aspect to it that oscillates like the forcing input. So here's an example differential equation. The right-hand side is not 0, so it's a forced differential equation. It turns out that this differential equation has a solution of this form, where the first term is the homogeneous solution and the second term is the particular solution. The homogeneous solution is based on the characteristic equation. It's the solution of the characteristic equation when the right-hand side is 0. So x double dot becomes lambda squared, 8 times x dot becomes x times lambda, and 25x is just 25. So again, we have a quadratic equation. We can find the roots using the quadratic formula, and it turns out that the roots are -4 plus or minus 3j. And if we think back to what those represent, when we have complex roots, we have a decaying sinusoid for the homogeneous solution, where the real part, the -4, tells us the rate of decay, and the imaginary part tells us the frequency of oscillation. Okay. So that's just like what we did previously. The particular solution has the same form as the forcing function typically. So in this case, our forcing function is a linear function of time. In essence, it's a line with a slope of 2 and a y-intercept of 0. And so our particular solution is also going to be a linear function of time. Y equals mx plus b. Looking at this, we can see that the homogeneous portion dies out. It sort of captures, it affects the transient behavior of the system. Since we have exponential decay, we're going to get a decaying sinusoid that decays to 0 eventually. But the forcing function stays. It doesn't die out. It will be there once the transient dies out. And so again, I don't expect you to have a great grasp of what transient steady state means, but these are concepts that are going to come back. When we talk about physical systems, we want to be able to characterize both the transient and the steady state behavior of the system. At this point, this is just the basic form of the solution, and this is pretty much the level that we're going to go to. We're just sort of trying to predict the character of the system. If you actually wanted to solve for these coefficients, the small a and the small b, you would plug the particular solution back into the differential equation, and that would allow you to solve for little a and little b. If you wanted to solve for the coefficients in the homogeneous solution, the large A and the large B, you would have to use the initial conditions. You would have to be told what the initial position is and what the initial velocity is. Let's now consider other types of forcing functions. So for example, instead of our system being forced with a linear function, let's say it's forced with a constant. So a constant force is applied to the mass. Since the left-hand side is still the same, we will still have the same roots of the characteristic equation. We'll still have the same homogeneous, the form of the homogeneous solution will be the same. But the particular solution, instead of being a linear function, will just be a constant, because the forcing function is a constant. And so we'll end up with a solution of that form. If the forcing function has the form of an exponential, we still have the same homogeneous part, but the particular solution now has the form of an exponential with the same exponent. And if we force the system with a sinusoid, if the force is oscillating with a frequency of 2 radians per second, then the mass is also going to, the displacement of the mass is also going to oscillate with a frequency of 2 radians per second. But that oscillation may be scaled, and that oscillation may also be shifted in time. There might be a phase shift. Another way that we can represent a sinusoid with a certain frequency and phase shift as the sum of a cosine and a sine wave. So those are equivalent depending on your choice of coefficients there.